Hello everyone, this is Engineer Mark Earl C. Amorin to present my machine problem 1 in Mathematics 221. So I have chosen topic set 2 which contains the following numerical methods. So secant method, Gauss-Jacobi, and Lagrange and Newton's interpolation. So to start with, I have used the C programming language to implement my 3 source codes or my programs. Why did I choose this C programming language? Because of its efficiency, it yields faster execution times, and because of its portability, because it can be used on different operating systems. So here is the general flow of a program for execution. So I have inputted my code or source code in a word processor, and then I have used a compiler named CodeBlocks to translate the source program into machine language. So the general form of a C program. So every C program must have a main function. This serves as the program's entry point and contains the code that will be executed when the program runs. So the main function has a specific signature int main. And then for the data declaration, you need to declare variables and their data types before using them. So this typically appears at the beginning of your main function or in the scope where they are needed. You also have your statements that perform actions or computations. So this can include assignments, control structures, your if, while, for. It can also be function calls and more. And you can also define your own functions in C to encapsulate reusable code. Functions have a return type, a name, and parameters if any. So to start with, let's discuss the solutions to nonlinear equations using numerical methods. So here are the general steps in finding the iterative solution. So first, we need to establish the formula for the unknown, substitute the given initial value to the formula to get the new value of the unknown, and then we need to check for 3 convergence criteria. So in my source program, I have implemented these 3 convergence criteria. So the first criterion is the number or the maximum number of iterations. The second one is the absolute value of difference between 2 consecutive values of the unknowns. And the third one is the absolute function value itself. So for the criteria 2 and 3, so this should be less than or equal to the tolerance value. For this case, I have chosen e to be 1 times 10 raised to negative 5. So secant method. So in secant method, we do not need for the derivative information of the function. Thus, it is faster in terms of convergence than other methods such as bisection, and you need fewer iterations for accurate results. So here is the formula to be used in the secant method. So here is a simple pseudocode for us to understand how we will implement secant method in our source code. So number 1, we need to define a function that takes a value of x and then returns the value of the target function. And in your main function, you should have initial values x0 and x1 as your initial guesses. And then you should also define a small value tolerance, which is your variable e, for your criterion of convergence. So initialize a maximum number of iterations, initialize an iteration counter I to 0, and then you need to print also a header for the output table later on. So inside your main function is a loop to calculate the new approximation of the root x sub 2 using the secant method formula. And then you need to check for convergence by comparing the absolute of x sub 2 minus x sub 1 to your tolerance value e. So if convergence is reached, so you need to print the approximate root and exit the loop itself. So for example, we have here a simple function f of x is equal to x squared minus 3x plus 1. And we need to find a root of this function using the secant method. And we should start from x sub 0 is equal to 1.2 and x sub 1 is equal to 1. And we note that by using our quadratic formula, we have the roots to be approximately 0.38197 and 2.61803. So since our initial values are within 1.2 and 1.0, hence our target root is this one, 0.38197. So here is the source code of the secant method. So the function, conveniently named function, defines the target function x squared minus 3x plus 1 in this case. We also have another function called derivative, which calculates a new approximation for the root using the two given points x1 and x2. And then another function, new x, which calculates a new approximation for the root using the secant formula, as shown earlier. If the derivative of this is 0, so it prints an error message indicating that the method cannot proceed. So in the main function, the code initializes the variables for the iterative process. So you have x old 1, x old 2 as the initial guesses for the root, and you have x new for the updated approximation. So E here is the tolerance value, 1 times 10 raised to negative 5. In each iteration, it calculates a new approximation of the root using new x function. It updates also the iteration count and then prints the iteration details. So it checks for convergence using two conditions. So the first one, if the absolute value of function x new is less than or equal to e, this indicates that the function value is very close to 0. And the second condition is if the absolute difference between x new and x old 1 is less than or equal to e, so we also stop the iteration. So if either of these conditions is met, the code prints the approximate solution, indicating convergence has been reached, and then it exits the program. So here is the output as shown in the executable file. So from iteration 1 to 6, so it prints the values of your x and also the values of your convergence criterion. And as we can see in iteration number 6, the solution converges to 0.38197. And this is verified by using the quadratic formula, so you get the same result. For the next topic, systems of linear equations. So here are the general steps to solve systems using indirect methods such as your Gauss-Jacobi. So let's make our matrix diagonally dominant and making sure that none of those diagonal elements are 0. So we need to establish formula for each of the unknowns using the given equations, then substitute the initial given values to the formula for the unknowns, and solve for the new values of the unknowns. And similarly, we also need to check for the three convergence criteria if satisfied. So why Jacobi method? Because this converges for a diagonally dominant matrix, and it only requires us the basic matrix vector operations. Thus, this method provides us a solution even when other methods fail. So here is the source code for the Jacobi method. So the code starts by defining two functions. The first one is sine, which returns a value that alternates between positive and negative depending on the sum of I and j. And the second function is determinant, which recursively calculates the determinant of the square matrix, matrix A. So the core of the code is the JIM or GIM function. It accepts the matrix A representing the coefficients of the linear system and vector B or mat B representing the right-hand side of the equations. And you also need the size of the system. So within this function JIM, initial values matx0, matx, and materror are created. So these arrays represent the current approximation of the solution, the updated solution, and the error in each component of the solution, respectively. So the code enters a loop labeled A, representing the iterations of the Jacobi method. So in each iteration, the current value of matx0 are printed as part of the iteration table. A new approximation for matx is computed using the Jacobi iteration formula. So the error in each component of the solution is calculated and stored in materror. The maximum error among all components is tracked as error. So after each iteration, the code checks if the maximum error is greater than a predefined tolerance. So if it is, the approximation in matrix X is updated to matx0 and the iteration continues. So this loop continues until the error falls below the tolerance, indicating convergence. So once convergence is achieved, the code prints the final solution. So in our main function, users are presented with a menu to choose between different iterative methods. So for Jacobi, the user should input 1. And after that, so he or she should also provide input data for the system of linear equations, including the elements of the matrix A and the coefficient matrix or the matrix B. So the code calls the GAM function within the provided input data and displays the solution once convergence is reached. So let's solve this system of linear equations using Jacobi iteration. So here are the inputs for the program. So the user should input the number of unknowns in our system. So in this case, 3. The user also needs to input the elements of the coefficient matrix or the matrix A, which is a 3 by 3 matrix. And also the elements of the constant matrix or the right-hand side, numbers which are 11, -1, and 5. So here is the output program for the Jacobi method. And as we can see, at the 9th iteration, the solution converges at the following values. X of 1 is equal to 2, x of 2 is equal to 1, x of 3 is also equal to 1. So we can verify this answer by using our traditional methods in algebra. And for the last part, so we have the interpolation. So interpolation means finding the approximate value of a function f of x for an x value between different values x naught, x1 up to x sub n, at which the values of f of x are given. So the objective of interpolation is to approximate a given function f from among other simpler functions. So typically we use polynomials. Why polynomials? Because they are easy to evaluate, differentiate, and integrate. So I have chosen these two methods to find or to approximate the value of f. So let's discuss the first method, the Lagrange interpolation. So it only requires us basic algebraic operations, so no need for complex mathematical functions or derivatives. So as an example, I have used the example as shown in machine exercise 1. So here we have given set of data points and our independent points or variable is x, and then our dependent variable is f. So we need to find the value of f at distance of x is equal to 12.5. So applying the source code of the Lagrange interpolation, so the code computes the Lagrange basis polynomial L for each data point, which are then used to calculate the interpolated value B at A. L represents the contribution of each data point to the interpolated value at A. So the code iterates through all data points. For each data point, it calculates L based on the formula of the Lagrange polynomial. The interpolated value B is the sum of the products of L and the corresponding value F, as shown on the screen. So the user inputs of this executable file is the number of data points, which is 6. And to input the data points, we need to separate X and F using space bar, as shown in the screen. So users are also asked to specify the value of X at which they want to interpolate the function. So in this case, X is equal 12.5. So here is the output of the Lagrange interpolation. So at x equals 12.5, the value of f is 9.172606. Now to verify if this answer is correct, so I have also implemented the Newton's divided difference method to check if the same results will be shown on the screen or in the source code. So Newton's divided difference, so it requires fewer arithmetic operations than the Lagrange form. So same example, so same user input, and here is the source code for the Newton's method. So the code calculates divided difference coefficients y based on the provided data points. It then uses these coefficients to construct the Newton interpolation polynomial. The interpolated value B is calculated by evaluating the Newton polynomial at A. So the K array stores intermediate values that depend on the specific A value and are used in the calculation. And as shown here in the output screen, F is also equal to 9.172606, the same result with the Lagrange interpolation. So here are my references to make this machine problem possible. Thank you for listening.